And the next talk is by Pablo Egea Hervas. Presentation here.
It's this one, the PowerPoint. No. Give it. Hi, good
Please go
morning.
ahead.
My name is Pablo Egea, and I will be presenting the work we've been carrying out in CET Ingenieros about the deep learning investigation for automatic control and system characterization for airborne wind energy systems. First, I would like to start with a quick introduction about the definition of this project and the goals and motivations. This project was part of the 2021 call for the research and development in artificial intelligence and other digital technologies, and was funded by the European Union and the Spanish government. And the main motivation was to combine the development on AWES and artificial intelligence, as they are the two fields very new, and there's very little work that combine the two. We also wanted to explore reinforcement learning applications in control for AWES, as we think it can be a solution for a robust and autonomous control in the variable conditions that these systems will operate on. Next, we will talk about the development of all that we have done. First, we would like to present the available means we had to retrieve our data. Then a quick commentary about some data-driven models that we developed. And after that, we would like to focus more on the reinforcement learning environments and the learning approaches that we defined. So as available means, we had first a testbed developed jointly with this university, which evolution you can see at the gates of the Congress. But at the time when we started the project, this was a 3-line machine with on-ground control, with some data acquisition system, with a Pixhawk, with GPS, and some dynamic data, some anemometer on ground, and some miscellaneous sensors. And also we had the load cells, both in air and on ground, to measure the tether tensions.
Yeah.
And also, on the other hand, we had developed also a simulator where we tried to mimic as much as we could the machine that we had available. So in this case, we have a simulation that simulates the dynamics, the navigation and control, and also has a model for mass in case there's some kind of morphing in the aircraft. But in this case, we use an aerodynamic model of the kite that has been developed also by this university. In the simulator, we have also an atmosphere model of the international standard atmosphere with wind model, a logarithmic wind law, and it can also include gusts that are modeled with a sinusoidal wave with a set probability of activation. So here, from those two sources, we had not very big actually data sets. So we had prepared 3 different data sets, one only from experimental data, one from simulated, and we also tried to do a mixture to develop a model that could behave well both under a simulation environment and a real environment. So we did some testing and developed some data-driven model, mostly based on multi-layer perceptron and gated recurring units. And we tried to develop 2 different models, one more general dynamic, but we didn't have enough data for that. So we focused more on a model that could predict the dynamics in a figure of 8 movement. So the first model we had we're using the multi-layer perceptrons with a mean square error of 2 to the minus 3 and an R square of 0.97. But take into account, here you can see in the graph, you can see, but that's scaled, so it might not seems very accurate. But you can see that we can predict fairly well the next step of the simulation. But when we try to isolate this model and only input information that comes out of the same model, it quickly drifted. So it cannot really be used as a substitute for example, a mathematical model or a real model. We tried to use this as a model in a model predictive control algorithm, but as we wanted to make a controller that could behave in real time, the computation times were too large, so we discarded this line of investigation. Another parallel line we made was the development of a reinforcement learning controller. So in general, a reinforcement learning controller trains an agent to predict an action that maximizes the return on every time t. In this case, we have the agent, that will be our controller. We have an environment that changes based on the action made by the agent, and the environment shares with the agent what is the next state, so the agent can know where he is in the next state, and the reward that measures how good or how bad that change was. In our case, we have two environments, as we have discussed, a simulator and a testbed, which will be interchangeable for our agent. And as agent, we have tested 3 different algorithms: a deep deterministic policy gradient, a twin delayed deep deterministic policy gradient, and a proximal policy optimization. In our case, the best results were staying with the twin delayed DDPG. Okay, but first, we need to establish a way to learn. So first, and based on what we see in UAV literature, most work center around following a trajectory. So we started from that. The trajectory we used was one created by a PID that is both implemented in the simulator and in the machine. And we tried to do something similar to what's in the literature for UAV, where we have as a state measurement of how far from the trajectory we are, but we have no actual information of the total state of the system. And as a reward, well, it's mostly a reward on how far you are from the reference, how different are the orientation, how different are the velocities. We also had a term for how smooth the control is. In this case, we trained DDPG, but we could not see any learning whatsoever. And we thought that maybe the observations were too obtuse for an agent to infer the behavior of the system. And we thought that maybe these problems, and given that the dynamics of the system are very quick, was too complex as a starting point. So we took a step back and thought about a different angle. So we established an incremental training approach and also changed the states that were fed to the agent. Here, the agent knows at any time where it is, what's the angular velocities, wind speed, wind direction, acceleration, and speeds at instant t and some other instance in the past, so it can infer the dynamics as we saw in the data-driven model. And as for learning approach, we thought we started with something simple and then build up from there. So the first thing a kite has to do is stay on the air, right? So first we trained the agent on air with steady wind. We tried a random series of wind direction and wind magnitudes, and we defined a reward where the system was rewarded if it stayed in an interval of elevation angles. It didn't reward nor punish when it goes above, as the kite's still in the air, and it punishes when it's below the lower limit with a square law. And then after it has learned to stay on air with a random steady wind, we added gusts, which means only changing the environment as the conditions are the same. The kite must stay in the air. And as a third step, as we didn't want to be very specific, we just included a term for the tension of the cables, which was one of the things we had available. And we did only like the mean tension value. And here we can see that for the height with a steady wind, it was able to stay on air on the simulation, of course, yet. As you can see, that's kind of a figure of 8, as it is kind of an equilibrium position. But when we added, after it was trained, added the term for the tension, we could see that the agent was able to point itself in the direction of the wind. And here also can see that the tensions, these are scale tensions between 0 to 1, and the tensions are in general, well, once it's stable, they are always greater than the height. So I would like to end with a quick summary and conclusions. So as a summary, we have developed data-driven models with reasonable accuracy for instant prediction, but not good enough to substitute mathematical models. And also we have developed a controller based on reinforcement learning that is capable of maintaining a kite on the air on a simulator without prior experience. And also the behavior of the controller when adding reward regarding the tether tension seems to indicate that it can somehow learn by its own. One possible way to not maximize this energy is also obviously depends on how you define the rewards, but it might indicate that it can learn things without very specific directions. As future work, we still need to test the adequation of the controller in the simulation in the real machine. We expect to do that in May. We have performed a little bit of testing, not only of the interface, and we need to do some real adjustments. And also we think that the application of reinforcement learning techniques in this case could be promising, but there is a further need of investigation and testing of different rewards combination, and we think it can be a good way to advance in this field. And also we would like to know that the development of this type of controllers need a kind of digital twin simulation environment for every machine, as you cannot train a reinforcement learning agent in this kind of machine because the kite will probably crash a lot of times. And that's not one thing that we can afford. So here you have some contact information. That was all, and thank you very much for your attention.
Thank you. Are there any questions? Yes, here. Wait a second, we need the microphone.
Please.
Hi, great talk. How do you think your controller, let's say we want to implement this on a system, how does this compare in terms of speed and accuracy to an, let's say, more classic approach like LQR based or PIDs or MPC? I don't know, like where does this compare?
This kind of controller is fairly straightforward. It's just a series of neural networks that only have to be followed once, so it's kind of a really quick thing to do. On operation, during training is a different story. But yeah, computationally it could be really, really fast.
Thank you.
And how does it compare in terms of accuracy and ability to
accuracy,
track?
we don't know. As I said, we think the best way to implement this is to define a general reward system and then let it do what it can. So I don't think it can be, as of yet, compared to any of the other control systems.
Thank you.
Thank you. Any more questions? Otherwise, we thank you. Yeah,
sorry, maybe you can comment on how difficult it was to get everything running, to get the learning to converge and so on, how much a priori knowledge you have to put into it.
Well, it was more time consuming than anything else. We did a lot of testing, and the training it takes a lot of time as our simulator works in real time, so we cannot accelerate that. We also need to pre-start the model with a PID because otherwise it crashes right when it starts. So I would say we needed about 1 million time steps. The time step is 1 millisecond. 1 million time steps to see anything relevant. But actually, you could see that it starts learning rather quickly. Maybe in 100,000 steps, it can start to maintain it in the air. Yeah, it's more time consuming more than anything.
Okay, thank
Thank
you.
you.
I think we need to stop now, so thank you again.